Hello everybody, today we will be talking about limits involving infinity. So this is going to be kind of like a part 2 of the limit things that we've been doing so far. So let's just see what we can cover for today then, okay? So as I mentioned, the topic for today is limits involving infinity. So let me just go ahead and kind of write that out over here. So limits involving infinity. And so what that means is that when we're looking at limits now, it could be the case where we're looking at x is getting closer and closer to positive or negative infinity, or it could be the case where the limit that we're trying to find involves infinity of some sort then. So to give an easy example, just to begin with, we'll look at the following. The limit as x approaches towards 0 from the right-hand side of 1 over x. Now, for those of you that might not know the graph, and I'm hoping that most of you guys actually do know the graph at this point, the graph of 1 over x looks something like the following. So here's the x-axis, here's the y-axis, and then it's going to be the following right there. So that curve, that's going to be y is equal to 1 over x. Now, because the limit in this case, we're looking at x approaching towards 0 from the right-hand side, that's what this little plus right here is representing, then that means that we're going towards 0 from the right-hand side. So we can see that it's coming towards this way. And as x gets closer and closer to 0 from that right-hand side, the limit then is going to be equal to infinity then. So that is going to be our first example. Now, at the same time, we can also say the limit as x approaches towards 0 from the left-hand side, indicated by that little negative above as a superscript, as a subscript then for 0 of 1 over x. And for the limit of this one, you can see graphically that it's going towards negative infinity because coming from the left-hand side, it's going downward. So that is going to be our answer. But if you remember from our last section, if we say, hey, if I'm trying to find just the limit of this, meaning limit as x approaches towards 0 of the function 1 over x, because the two limits from the left and the right are not agreeing with each other, then that means that the limit itself does not exist. Okay, simply put, in order for a limit to exist, the limit coming from the left and the limit coming from the right has to be the same thing. So just keep that in mind. And in fact, let me just go ahead and write that down right now. Limit as x approaches towards a from the left of f of x has to be equal to the limit as x approaches towards a from the right of f of x is equal to the limit as x approaches towards a itself for f of x. Okay. So let's take a look at some other examples involving limits and infinity then. Let's say this time around we have the limit as x approaches towards 2 from the left-hand side of x minus 2 divided by x squared plus x minus 6. Now, this is a typical problem from Algebra 2 where you're given a rational expression and you want to simplify as much as possible so then you can see what's actually happening. So what I'll do is I'll go ahead and do that. Limit as x approaches towards 2 from the left of x minus 2. And the bottom looks like it's factorable. It becomes x plus 3 and then also x minus 2. Sometimes an indication that you want to look for is the factor that is above right there. That's simple. You would most likely expect that to be a factor that's in the denominator. So that's kind of a hint towards as to how to actually factor this quickly. So the x minus 2 cancels out, and what we're left with now is the limit as x approaches towards 2 from the left-hand side, and we are left with 1 over x plus 3. Now, the graph itself of the limit as x approaches towards 2 from the left-hand side of 1 over x plus 3. First, let's go ahead and graph that out on the side right there. Okay. At x equals to negative 3, we have a vertical asymptote. So vertical asymptote located at x equals to negative 3. So that means graphically, we have a big vertical line like this that the graph can't actually touch. Whereas for the rest of the graph, well, it's just going to look like like a curve, just like what we had over here for 1 over x then. Okay, so in essence, it's basically just like our previous graph of 1 over x, except it's shifted over to the left by 3 units. So the graph would look something like the following right here, and also right here. Okay. Now, looking at what happens when x is approaching towards 2 from the left-hand side. So around 2, that's over here. And you can probably see graphically that 2 is something that I can actually now plug in. The graph, I do apologize. I just realized I messed up on one part. At x equals to 2, we actually have a removable discontinuity. So let me go ahead and write that out. Removable discontinuity. And what that means is that x is equal to 2, we actually have an open circle. But because we're looking for the limits, this right here is actually okay, because I just want to know graphically as to what is y is approaching towards as x is getting closer and closer to 2. So in order to find out what that value of y is equal to, we again think about what we did last time, which is try to plug in 2, if possible, into our simplified equation, because we couldn't plug it into our original equation. Plugging in 2 right now into that equation, we are going to get 1/5 as an answer. And yeah, that's basically what it looks like then. So coming from the left-hand side, you can see that it's getting closer and closer to 1/5. So that right there is another example of a limit problem then. Now, let me just go ahead and take this and change it a little bit. Suppose that we have the same problem, but this time I'm asking for limit as x approaches towards -3 from the left-hand side of x minus 2 divided by x squared minus x, plus x minus 6. If we go through the same procedure, then all of the characteristics and all of the algebra will still be the same. So in the end, according to what we did right above it, you would just get the following. Limit as x approaches towards -3 from the left of 1 over x plus 3. And again, we now look at what happens graphically, or if you want to, you can plug in values of 3 that is close to 3 from the left-hand side. So for example, maybe like say x is equal to 2.9 or x is equal to 2.99 and so on, so on, so on. The result is that according to the graph, this is going towards -infinity then. Okay. One more example of this type of limit, of this infinite limit, and then we'll go into a different topic, or actually a different a portion of this lecture. Let's say now we have limit as x approaches towards pi over 2, and then it's positive, meaning coming from the right-hand side, of tangent of x. Now, again, all of these graphs that I am providing for you, or all of these equations that I'm providing for you, these are graphs that hopefully you remember how it actually looks like according to Algebra 2 or Pre-Calculus or Trig or whenever you took this. So I'm going by that assumption. And for some reason, if you don't know what the graph looks like, you could technically go ahead and use a graphing calculator just to help you out. But preferably, it'll be ideal for you guys to memorize them. So for the graph of tangent, here is what we get then. We have vertical asymptotes at a lot of different places. One of them specifically is at pi over 2, where we're trying to find the limits. Another one would then be -pi over 2, and the period supposedly for tangent is supposed to be every single pi. So at those values of pi over 2, -pi over 2, 3 pi over 2, and so on and so on and so on, we have vertical asymptotes. Now, for the rest of the graph, we can go ahead and plug in values if you want, but I remember that at x equals to 0, tangent of 0 is equal to 0, so that means it goes to the origin. At pi over 4, tangent of pi over 4 is supposed to give you 1, so that means it goes to this value right here, this coordinate. And then finally at -pi over 4, then the tangent of that is going to be -1. So graphically, it looks something like the following then, okay? And the rest of the graph for tangent, it'll look exactly the same thing. But what I really want in the end is really what happens when x is approaching towards pi over 2 from the right-hand side. So that means it's coming towards pi over 2 from the right. And as you can see, the graph is now going towards -infinity. So that right there is going to be my answer. Okay. All right, so now let's look at limits with infinity from a different perspective. This time, let's say that I want to solve for the limit as x approaches towards infinity for a function. So meaning the result is not infinity, but instead what happens when x is going towards a really large number, or maybe like a large negative number. So again, just as a starting point, let's look at limit as x approaches towards infinity for 1 over x. Again, the graph from the very top, and for some reason I cannot see it too well right now because of the smudge, is supposed to be the following then. This again is going to be our graph of 1 over x. So you can see graphically that as x gets closer and closer to infinity, meaning the denominator is getting bigger and bigger, the result is that this is going to get closer and closer to 0. Similarly, we have limit as x approaches towards negative infinity of 1 over x, and that in itself is also equal to 0. So you can see that graphically as well. If I raise it to an exponent, meaning if I had something like, say, limit as x approaches towards infinity of 1 over x to the third, the idea is still the same thing. X cubed is going to be a number that is going to be really, really large. So when you take its reciprocal, the result is still equal to 0. And similarly, if I say x approaching towards negative infinity for 1 over x cubed, that is also going to yield 0 then. So the conclusion that I would like to get is the following then. If you have the limit as x approaches towards positive or negative infinity of the graph or of the equation 1 over x to the n, where n is supposed to be greater than 1, and the result is that the limit is approaching towards 0 then. Anything that is less than 1 for n, the result is that you're going to get something else. So we have to watch out for that restriction. So let me go ahead and write it down one more time. N is supposed to be greater than 1 in this case, or greater than or equal to 1. Okay. All right. Let's see. I think we can actually work something out for this one also too. In another sense, if I say limit as x approaches towards infinity for x to the n, where n is going to be a number that is greater than 0 in this case, then the result is that it's also going to be something that hopefully we will know. For example, if I have x squared, or if I have x to the third, or x to the fourth, or x to the 7.1, or maybe let's say x to the 0.5. All of these guys right here, as x gets bigger and bigger, the result is that you're going to get a y value that's going to be bigger and bigger and bigger too. So for the limit of this guy, the limit is supposed to be equal to infinity in this case then. And for the case of negative infinity, well, that's going to be a little bit trickier because it really depends on what n is equal to. So we're going to have to look at that case by case. Okay. So let's go ahead and set this on the side for the time being. We're going to definitely be able to use that in a little bit. Okay, let's consider the following then as an example. Okay. Let's say we have limit as x approaches towards infinity of 5x cubed minus 3x, all divided by 2x cubed plus 1. So for this rational expression, I want to find out what the limit is as x gets bigger and bigger. The best way in order to figure this out algebraically is to take the numerator and take the denominator and divide it both by the largest monomial that is present. So in this case, I want to divide both the top and bottom by x to the third. Okay. So watch what you'll get now algebraically then. So limit as x approaches towards infinity. The first piece in the numerator, 5 times x to the 1/3 divided by x to the 1/3, that is just strictly equal to 5, minus 3 times x divided by x to the third, that's going to be 3 divided by x squared. In the denominator, similarly, if you multiply 1 over x cubed inward, the first part is going to be 2 times x cubed divided by x cubed, that is just strictly equal to 2, plus 1 over x cubed because, well, 1 divided by x cubed, that's basically what you get right there. And in this form, you now can apply what we just said earlier about limit as x approaches towards infinity when you have a fraction where x is in the denominator. Note how we have 3 over x squared and also 1 over x cubed. So if I apply the limits to these, then you can think about what we just said earlier. 5 is not going to go anywhere. The second part right here, as x gets bigger and bigger, then 3 over x squared is definitely going to get smaller and smaller, and as a result, it's going to go towards 0. So we can replace that with 0. In fact, let me just go ahead and erase this part because we applied the limit already. Whereas for the bottom part, the 2 is still going to be a 2. But for the last piece, the limit as x approaches towards infinity of 1 over x cubed, that is also going to be equal to 0. So all I'm really doing is I'm just applying the limit law that we just came up with over here on the upper part. So finally put it all together, then that means the limit is equal to 5 over 2. Let's try to look at a couple more examples, and then afterwards I'll just let you try it on your own. This time, let's say limit as x approaches towards negative infinity of 9x to the 4th plus 2 divided by 7x to the 5th and then plus 6x squared and then minus 1. Again, let's take the same idea. We'll divide both top and bottom by the largest monomial, which in this case is 1 over x to the 5th. Okay. So limit as x approaches towards negative infinity. Of the top part, we get 9 over x. Then we have plus 2 divided by x to the 5th. All divided by 7 plus 6 divided by x to the 3rd minus 1 over x to the 5th. And again, the purpose right now is to, or the objective right now is to get your equation so that it is combined with a whole bunch of mixed fractions. Sorry, not mixed fractions, but like fractions within the fractions, so you can apply the limit law that we just have. Anytime you see x in the denominator, we can say that as x approaches towards infinity or negative infinity, those are going to go to 0. So then thinking about what we just did earlier, then we would get 0 plus 0 divided by 7 plus 0 minus 0. So the answer is that the limit as x approaches towards infinity, negative, is going to be equal to 0 then. Okay, so hopefully that's not too bad. Let's see. Let's try this one right here. This one is going to be our last example. And we're going to try to make this a little bit trickier just so that you can, see the variations here. So limit as x approaches towards infinity of 2x divided by the square root of 16x squared plus 1. Now, the square root is what's throwing some people off, but it's okay. Keep in mind that for the most part, when you take the square root of x squared, the result is that equal to x, okay? But this right here, again, that's only for x is greater than 0. So what that means is if I want to simplify just like the way that I did, again, first I'm going to go ahead and do the following. Divide both the top and bottom by the largest monomial, which in this case is supposedly 1 over x, because if you think about the top and the bottom, the square root of x squared, well, that's really just the same thing as 1 over x then. Let me write that out so you can see what I mean. So I'm going to go ahead and divide by 1 over x to both top and bottom, okay? And if I rewrite that, this is how we're going to actually bring it inside to the fraction. So 2x divided by the square root of 16x squared plus 1. The top part is still 1 over x, but according to what we just said over here, 1 over x, I can now rewrite that as 1 over the square root of x squared. And just like that, we can now put everything that we have in the inside. So limit as x approaches towards infinity of the top part multiplied out, that's just equal to 2. Divided by the bottom part, if I take the inside expression and divide by x squared to everything, the first part, I'm going to get 16. The second part, I am going to get 1 over x squared. So now again, we can go ahead and say let x approaches towards infinity. So when we try to apply it now, we're going to get 2 divided by the square root of 16 plus 0. So that gives us 2 over 4, which is the answer is equal to 1/2. Okay. Now, the one part that you might or might not consider is this right here. Take the same problem, but this time I'm going to say apply it to negative infinity. So 2x divided by the square root of 16x squared plus 1, but as x approaches towards negative infinity. Yes, this fraction right here, or actually not this fraction, this expression right here is true so long as x is greater than 0. But if x is less than 0, because looking at our limit right here, because x is approaching towards negative infinity, so that means the values of x that you're plugging in, it has to be negative. Well, for our expression, we have to change that a little bit. Or for our equation, we have to change that a little bit. The square root of x squared is equal to not x, but rather negative x if x is less than 0. Here, let me give you an example then. Okay, let's say that x is equal to negative 3. So we have the square root of negative 3 squared, which is then going to be equal to the square root of 9. And then because it's the square root of 9, the answer is equal to positive 3, not negative 3, because we didn't start with the square term. And on the other side, remember, I want it to be equal to x. And since x is equal to negative 3, then that means we have to throw a negative in front of it in order for that to actually work out. So here, let me just kind of write on the other side, negative 3 is equal to negative 3, and then it's equal to 3. Okay. So the way that it works out with this problem is when you apply that 1 over x thing, limit as x approaches towards negative infinity of 2x divided by the square root of, let's see, 16x squared plus 1. I think I jumped the gun a little bit. Previously, we said we're going to go ahead and do the following. Divide both top and bottom by the largest monomial, which is 1 over x once again. But when you now change what we have in the denominator, the 1 over x, your replacement is not just 1 over square root of x squared. It's going to be negative 1 over square root of x squared because of what we just said over here. Remember, again, x is approaching towards negative infinity. So now when we apply everything in, you'll see that the algebra is still the same as what we have above. We will have 2 divided by, but the one thing that's going to be different is now there's going to be an extra negative right here. And then it's going to be the square root of 16 plus 1 over x squared. So now applying the limit, we're going to get 2 divided by negative square root of 16 plus 0. So that gives us 2 divided by negative 4. So the answer is equal to negative 1/2 then. All right, so that should do it. I will see you guys next time and stay safe.